Hello and welcome to the second part of Lesson 1 in Unit 2A, Right Angle Trigonometry. This is Similar Triangles and Proportional Reasoning. So we started this lesson by looking at sort of a prerequisite skill, working with ratios and proportions and how to find missing values given a proportion. Then we went on to discover that similar triangles have certain sets of characteristics we can rely on to inform us when those two triangles are similar. And we've written them down here. It can be that all three corresponding sets of angles are equal. It could be that all three corresponding sides are in proportion to each other. And it can be that two pairs of corresponding sides and are in proportion and the contained angles are equal. That's something we're going to look at a little bit later. We're kind of focusing on the first two right now. And we did an example that supported this idea that similar triangles have sides that are in proportion. In fact, we were given two triangles here in example 1. We set up the sides, the corresponding sides, as ratios and determined what the actual scale factor was. Turned out 0.8, 0.8, and 0.8. So we did have two similar triangles here, which we then went on to state in our conclusion. Now we're going to look at another example. This is a word problem. This is like a total perfect it's a test question. This one's wonderful. So it reads, Elliot's summer employer asked him to find the height of a tree. He measures the length of the shadow of a meter stick to be 1.3 meters and at the same time the length of the shadow of the tree to be 14.8 meters. Find the tree's height to one decimal place using similar triangles. Make a diagram. So I've started a diagram here for us, and as we go on I'm going to explain just a little bit about what makes the triangles in this question similar, and then going on to use the proportions to find the missing values is a pretty small leap. So let's have a look. Questions dealing with trees and meter sticks. I've also taken the liberty of drawing in the sun since you're not going to get any shadows on the ground without a sun. The pieces of information we've been given are that the meter stick, which of course is 1 meter tall, has a shadow at this moment that is 1.3 meters long. And similarly, we have the length of a shadow of the tree to be 14.8 meters. So how are these similar triangles? That's a really good question. I'm going to just sort of sketch it over top, the idea that we're going to be driving at here. So if you can imagine, this tree is set up here, and then we have a shadow that leads down to the end. Similarly, you have this meter stick that goes up, and then this shadow that sort of comes down over here and connects. So we've created these two triangles. The first angle that we have that we're going to assume is similar is that both the tree and the meter stick are connecting at 90 degrees to the ground. Now, is that a bit of an assumption? It is. Obviously, they might not actually be at 90 degrees to the ground, but that's a safe assumption to make in a question like this. The second piece, and this is the one that takes a little bit of figuring, is that when a shadow hits a vertical object and then casts that shadow on the ground, that sun is connecting with the tree at a particular angle right here. And that angle is the same on all vertical objects at that moment, which means that we have two sets of angles in this triangle that we can determine are the same. The first, these 90 degrees that sit in the corners. The second, whatever this angle is here, the point of contact with the sun with this vertical object. And one of the neat characteristics of triangles is that if you have two out of the three angles, you know for certain that the third one will be equal, just because there's only three. So if the two pieces are identical that you're taking away, it also tells us that this angle and this angle are going to be equivalent as well. So using three angles, we've proven that these two triangles that we've set up are indeed similar. Now we can go on to find the piece of information that we're missing. The piece of information that we're missing is right over here, height of the tree. So let's go on to set up a couple of ratios here as a proportion. So what I'm going to suggest, I'm going to change up my colors here a little bit. I'm going to suggest that we do height over shadow in the big one. So let me change up my color here. So height over shadow will be x over 14.8. And I'll just make that little sort of note over here. That's height over shadow. And then we're going to do the same thing for the second triangle. We're going to do height over shadow. So height over shadow. And now we have something that looks an awful lot like a proportion with a missing piece of information that we can go on here to solve using cross multiplication. So we have 1.3x is equal to 14.8. We isolate x by dividing both sides by 1.3. x is then equal to, let's grab a calculator and figure this out, 14.8 divided by 1.3 is going to equal 11.38. So 11.4, I think we were working in meters here. Here we have an opportunity. This is a word problem, and we need to include a therefore statement. So therefore, the tree is 11.4 meters tall. There we go, summing it up. And that is how you use two similar triangles in like what I would call like a shadow style question to find a missing piece of information. Hopefully that makes sense. As I said, fill these notes out really well. These are going to be your reference when you go to work through your homework. Let's look at one more example here. We're going to prove that triangle ABC, so here we have triangle ABC and then connected, is going to be similar to triangle DEC. So then we're going to solve for the missing side lengths of CD, which is this guy here, as well as CE, which is going to be this guy here. I've just called them X and Y. You can call them whatever you like. So I think the first thing we want to do here is look and see, are these actual triangles similar? I'm going to draw your mind back to some of the things you learned in grade 9 about sort of properties of angles. One thing that we know about properties of angles is that when two straight lines cross, their opposite angles are going to be equal. So this angle here will be equal to this angle here. So we've proven that two angles are already identical. The next thing I'd like to draw your attention to is the fact that we've been given two sets of parallel lines, or a pair of parallel lines. And one thing we remember about parallel lines is that there's all sorts of fun little patterns we can do with them. For example, this guy here, which you would have called in grade 9 probably the Z pattern, it means that this angle here, A, is going to be equal to this angle down here, D. And as before, if we have 2 out of the 3 angles in any triangle being the same, we know necessarily that those third angles will also be the same. And I'll put, I don't know what to put in that corner. Maybe I'll just do like one little scoop there as opposed to one that's colored in. There we go. So we've proven that triangle ABC is similar to triangle DEC. We did this using, again, as we did with the triangle in the question before with the trees and the shadows, we did this using 3 angles, and now we're being asked to solve for CD and CE. Now first things first, what I'd like to articulate here is an actual similarity statement, because these triangles, the way that they're set up, it's a little bit confusing to see them, and what I'd like to do is take this opportunity to kind of rotate one of them for you. So imagine I'm talking about this triangle over here. This guy here, it's not configured the same way as triangle ABC. It's kind of upside down on its head. So what I'd like to do is maybe just sort of sketch it down here. It's kind of the bigger version of that one, and we've just reorganized it. Essentially what I've done is I've just kind of like rotated around, so this part here has now just kind of come around and become the bottom. So what we have up here at the top, let me change up my colors here, this is going to be angle D. And again, if you can imagine that rotation in your head, this will be angle E and this will be angle C. And now we can start to fill in some side lengths that we do know. So we know that side ED or DE is going to be 5.4. And then I was previously calling side CE Y, and I was calling side CD X. And again, if I was going to draw those shapes back in, which I guess I'll do because we're here, we've got this angle here being the same, this angle here being the one that I colored in, and this one here being the little dot. So hopefully you can visualize that. It's complicated, I think, to sort of sometimes shift things around in your brain like that. But as we rotate that, now at least the triangles are lined up visually in a way that I can see, okay, this will be easier to set up the sides that are going to be equal. So for example, if I have side AB over side DE, so that's its corresponding side, right? We did AB and then we did DE, and now I'm going to set up, let's go get X first. So let's do AC, and this would be DC equals AC over DC. That's funny. So AB is going to be 3.6, DE is going to be 5.4, AC is going to be 4.1, and DC is our unknown, which we were calling X. Again, we've set up a nice little proportion here. Let's do some cross multiplying. So we have 3.6 times X, or 3.6X, equals 5.4 times 4.1. And how do we get that X alone? We divide both sides by 3.6. So we have then X is equal to approximately, and I'm going to type this in, so 5.4 times 4.1 equals, divided by 3.6 equals, and that came to 6.15. So I don't know if it told us what to round to, did it? No, it doesn't say. So we'll go to 2 decimal places since it did terminate, it did end, and we'll call that centimeters. Now we're going to set up that last one. So the last one, same idea, we're going to use A, B, and DE again. And that's just in case we made a mistake in figuring out what side DC is equal to. So we're going to do AB over DC is equal to, and this time we are going to do BC and EC. BC and, oh wait, that's not right. BC and EC. Oh yeah, that's right. EC. Sorry, I'm just looking at this. I think I've made an error in here somewhere. Hold on. I gotta set that up again. So I'm looking for the AB and DE. That was my error right there. So we have AB to DE, and then we're going to go BC and EC. There we go. Much better. Okay. So now we're going to substitute in the values that we know. Again, that was 3.6 and 5.4. Side BC this time, if I look up, is going to be 4.5. And side EC, that's going to be the Y. Let's set up to cross multiply. Here we go. We have 3.6 Y is equal to 5.4 times 4.5. How do we isolate Y? Divide both sides by 3.6. Y then is equal to approximately, actually I guess the first one was not approximate, it was exact. And let's see if this one's going to be approximate either. So we've got 5.4 times 4.5 equals, divided by 3.6 equals, also an exact value, 6.75 centimeters. And there we go. There we have it. So this lesson hopefully has shown you a few things. First, a reminder on how to find missing values in proportions. And then the whole thing that we learned, how to determine that triangles are similar, how to write a similarity statement, and then how to go on to set up sides that are in proportion so that you can find missing values. Big lesson, I know. Take a crack at that homework. It's just hanging out here at the bottom. If you have any questions, always reach out. I'll give you some guidance if I can in person or via a video or some direct contact, whatever works best. So good luck with this homework, and we'll see you in lesson number 2.